Hello to everyone who is watching this video. This is Ashkan, and in this video I will be presenting about ammonia production. Now here's how I have categorized my topic, starting with what is ammonia, going with ammonia production industry, steam A reforming process, overall reaction, desulfurization, primary and secondary reforming, shift conversion, methanation, and finally Haber-Bosch process. Now, what is ammonia? Ammonia is a molecule consisting of nitrogen and hydrogen covalently bounded with an angular bond of 107 degrees with a molecular formula of NH3. These colorless gases contributed significantly to the nutritional and pharmaceutical needs of people around the world. Have you ever asked yourself, with 6.92 billion people around the world, how does the food production industry is able to feed all of them? Well, the answer lies in the huge role of ammonia on food industry. Approximately 83% of ammonia produced around the world is used as fertilizers, either in the salt form or as solution. So there are currently two main types of ammonia production process in operation around the world. The first one is the steam reforming of natural gas or other light hydrocarbons, for example, natural gas liquids or liquefied petroleum gas. And the other pathway is partial oxidation of heavy fuel oil or vacuum residue. About 85% of world ammonia production is based on a steam reforming process. As you can see in this slide, this is Gujarat State Fertilizers and Chemicals, located in Gujarat, India. And in this slide, you are seeing Burrup Fertilizers plant in Western Australia, which can produce 760,000 tons of liquid ammonia per year. Before starting to go to the actual process of ammonia production, let's refresh our memory on three important principles. First one, the effects of catalysts on rate of reaction. A catalyst speeds up the rate of reaction either by allowing a different reaction mechanism or by providing additional mechanisms. The overall effect is to lower the activation energy, which means the rate of reaction. The second principle, the effect of pressure on the rate of reaction. In order for any reaction to happen, those particles must first collide. This is true where both particles are in the gas state, or whether one is a gas and the other is a solid. If the pressure is high, the chance of having successful collisions are greater. The Chatelier's principle. The Chatelier's principle states that a dynamic equilibrium tends to respond so as to relieve the effect of any change in the condition that affect the equilibrium. The two important concepts of this principle applied to the ammonia production are the following. First, in an exothermic reaction, decreasing the temperature would result the equilibrium to shift toward the product. And the second concept, when there is fewer gaseous product molecules than reactant gaseous molecule, increasing the pressure would force the equilibrium to shift toward the product. Now that you have refreshed your mind on these three principles, I will start explaining the ammonia production process. Starting with natural gas coming through, the second part is desulfurization, going with primary reformer, secondary reformer, shift conversion, CO2 removal, methanation, compression, and finally ammonia synthesis. Starting with the overall reaction. In order to produce ammonia, hydrogen gas and nitrogen gas need to be presented. However, because there is not sufficient hydrogen supplies in the air, the hydrogen gas needs to come from another source, which in this case is methane. The overall reaction consists of methane, air, and water as reactants, which would produce carbon monoxide, nitrogen, and hydrogen. The nitrogen and hydrogen is then used to produce ammonia. Since methane gas contains a little bit of sulfur oxide and hydrogen sulfide impurities, this step, which is the step of desulfurization, is necessary because these impurities would poison the catalysts that are used further in the next chambers. and at the end the zinc sulfide remain in the absorption bed and will be removed from methane. Primary reformer. The steam gas mixture is then heated further to 500 to between 500 to 600 degrees Celsius after desulfurization. But because the reaction is highly endothermic, the additional heat is required, so the temperature would be raised to a temperature between 780 to 830 degrees Celsius at the reformer outlet. The reformer consists of iron-containing reforming catalysts. So this is the first part in which catalysts are coming into action. Catalyst has no effect on the position of chemical equilibrium. Rather, it provides an alternative pathway with lower activation energy and hence increase the reaction rate, while remaining chemically unchanged at the end of the reaction. The first Haber-Bosch reaction chambers use osmium and ruthenium as catalysts, however. Under Bosch's direction in 1909, a much less expensive iron-based catalyst was discovered that is still used today. Part of the industrial production now takes place with a ruthenium rather than an iron catalyst because this more active catalyst allows reduced operating pressures. Moving on to the secondary reformer. Only 30 to 40% of the hydrocarbon will react in the primary reformer. So the secondary reformer is needed to have the rest of the unreacted hydrocarbons blended with air for additional yield of hydrogen gas. Now moving on to the shift conversion. In the shift conversion process, the reforming process will produce undesired carbon monoxide, which needs to be removed. This is what happens in shift conversion. The gas is passed through a bed of iron oxide and chromium oxide catalyst at around 400 degrees Celsius, which is called the high temperature shift conversion, or HTS. CO2 removal. The carbon dioxide is then removed by absorption in aqueous ethanolamine solutions. As you can see in the diagram, the carbon dioxide and water are being removed out of the process. Now the next process is methanation. Still, there is a small amount of carbon monoxide and carbon dioxide remaining in the process, which need to be converted to methane. The reaction takes place at around 300 degrees Celsius in a reactor filled with iron-containing catalyst, as you can see in this diagram. And now, moving on to the final step, which is the Haber-Bosch process. To produce the desired end product ammonia, the hydrogen is then catalytically reacted with nitrogen derived from process air to form anhydrous liquid ammonia. This step is known as the ammonia synthesis loop, or as we call it, the Haber-Bosch process. Now there are two important factors laying in this process. First one is the Le Chatelier's principle for higher yield of ammonia, and then the effect of pressure on rate of reaction. The ammonia production reaction is an endothermic reaction, thus heat releases as the reaction proceeds. The Chatelier's principle predicts that the yield of ammonia is greater at lower temperature. This way there is more ammonia produced. However, this would make another huge problem. Low temperature would decrease the rate of reaction. This is crucial when we examine the business issues associated with the company producing the ammonia. Now, combined with Le Chatelier's principle, the effect of pressure on rate of reaction comes into the action. At high pressure, the rate of reaction will increase according to the collision theory. The high pressure would cause more successful collisions, therefore the rate of reaction would be increased. Consequently, the pressure would also affect the equilibrium of the ammonia synthesis reaction. According to Le Chatelier's principle, the yield of ammonia is greater at higher pressure. High pressure will contribute to two important factors. First, it would increase the rate of reaction, which was originally decreased by the low temperature, and then it would forcing the equilibrium, shifting it toward the products. However, high pressure plants are expensive to build and maintain, however, A German chemical engineer, Karl Busch, solved this problem by designing a double-walled steel vessel that could operate at several hundred times atmospheric pressure. Modern plants operate at pressures in the range of 2000 kilopascals to 3000 kilopascals. The gas mixture is kept pressurized in a condenser, and ammonia is removed from the reaction vessel by cooling the mixture. Because of the hydrogen bonding between ammonia molecules, the gas condenses into a liquid while the nitrogen and hydrogen remain as gases. Nitrogen is removed to shift the equilibrium toward the production of more ammonia. Once the ammonia is removed, the gas are recycled back to the reaction vessel in a continuous operation. As you can see in this emphasized part of the diagram, this is the part where the unreacted nitrogen gas and hydrogen gas is getting back into the reactor to be processed and reacted again to produce more ammonia. And this was my end of my presentation in this video, and here are my references that I have used for the information that I get. I hope you enjoy this video.